Welcome students, now we are going to see some theorems on Cauchy sequences. But before that, we are going to see now this theorem. Now this theorem tells us about the convergence of a subsequence. Okay, that is, when the given sequence is convergent, then its subsequence is also convergent in a matrix space. So statement of the theorem is let x comma d be a matrix space and xn be a convergent sequence in matrix space x comma d. Yes, x comma d, such that xn converges to x here. If xnk is any subsequence of xn. Now xnk is subsequence of this sequence xn, then xnk converges to x as k tends to infinity here. Now it means that now here if the given sequence is convergent, then its subsequence is also convergent and converges to the same limit x here. Now proof of this theorem is this. So proof. Now here this is the convergent sequence here. So we write here let xn be a convergent sequence in a matrix space x comma d such that xn converges to x as n tends to infinity here. Okay, then for each epsilon greater than 0, because by using definition of convergent sequence we write then for each epsilon greater than 0 there exists a positive integer capital N such that we write here distance between xn and x is less than epsilon for all n greater than or equal to n here. Now we want to show that here now this subsequence xnk of xn is convergent. So if k is greater than or equal to n, okay, then we write nk is always greater or equal k. Now we prove this by induction. So using this we write here so that now k is greater than or equal to n here and nk is greater than or equal to k here. So we write here nk is greater than or equal to n here, and thus we write here distance between now x and k. Now x and k is the subsequence of the sequence xn here. Now this subsequence is formed by using the terms of the sequence xn here. So we write here distance between x and k and x. Now this is less than epsilon for all k greater than or equal to n here. So this implies that here this subsequence x and k converges to x as k tends to infinity here. Now here we have proved that now this subsequence x and k converges to x as k tends to infinity here. But remember that, student, okay, if the subsequences are convergent, then it doesn't mean that the original sequence is convergent. That is, if a subsequence of a sequence in a metric space is convergent, then the sequence itself need not be convergent. So if you consider this, so example is this example. Now consider this sequence, consider the sequence xn, which is -1 raised to n in usual metric space Ru. Okay, now if you consider subsequence of this sequence, that is this subsequence, the subsequence x to n, okay, x to n is now -1 raised to 2n. So we write here, so x to n, that is 1 here, okay, of xn, okay. Then in this case, now this subsequence x to n, now this converges to 1 as n tends to infinity here, okay. Now here, now this subsequence x to n of xn converges to 1 as n tends to infinity here. But the sequence xn, now xn is now here, now in this case -1 raised to n, okay, -1 raised to n. Now this is oscillating sequence, so therefore now this sequence is not convergent, okay. So xn is not convergent here, is not convergent. Now after that we are going to see this theorem here. Now this theorem tells us about the convergence of the sequence and its subsequence. So here the sequence xn is convergent if and only if it has a convergent subsequence, but only that condition is not here. One more condition is that sequence should be Cauchy sequence here. So statement of the theorem is that let xn be a Cauchy sequence, xn be a Cauchy sequence in a metric space, x comma d, then sequence xn is convergent if and only if it has a convergent subsequence, if and only if it has a convergent subsequence. Now to prove this theorem, now here, now we are going to consider this, that is, now in this case we are going to consider here, now if x and k is convergent, okay, that is subsequence is convergent, then the sequence is convergent here. So to prove this, we consider this sequence. So we write here, let xn be a Cauchy sequence, in a metric space, x comma d, and x and k. Now this is the subsequence of sequence xn here, okay, x and k be a convergent subsequence of xn. Now xnk is the convergent subsequence of xn here. Now suppose that now since xnk is convergent subsequence, so we consider limit of that sequence as x. So suppose that xnk converges to x as k tends to infinity here. Okay, then by using definition of convergent sequence, then for each epsilon greater than 0, there exists a positive integer capital N, positive integer, now here capital N, such that now distance between x and k and x is less than epsilon by 2 for all n suffix k greater than or equal to n here. Now we have here, now this sequence xn is a Cauchy sequence here, so we are going to use this. Also xn being a Cauchy sequence, here we have distance between now x and k and xn. Now this is less than epsilon by 2 for all n and n suffix k greater than or equal to n here. Now since xd is matrix space and all these elements are in a matrix space xd, so we write here, hence we write now distance between xn and x. Now this is less equal distance between xn and xnk plus distance between xnk and x. We write this by using triangle inequality here, by using triangle inequality. Now using this and this, so we have these two, so we write here, therefore distance between xn and x. Now this distance, okay, distance between xn and xnk is less than epsilon by 2, so we write here less than epsilon by 2 plus now distance between xnk and x, now this is also less than epsilon by 2, so we write epsilon by 2 plus epsilon by 2, so which is epsilon for all here n greater equal n. So this implies that here xn converges to x here. Now this implies that here xn converges to x as n tends to infinity here. Okay, now to prove the converse part here, now we are going to use the same proof here which we have studied earlier, that is for converse part. So conversely we assume that here the sequence xn converges to x as n tends to infinity here. Now we want to show that here, now that subsequence xnk of xn is convergent here. Okay, so we write here then for each epsilon greater than 0, okay, there exists a positive integer n such that we write here distance between now xn and x is less than epsilon for all n greater equal n. Now if we take integer here k, greater than or equal to n. Okay, then by induction now we prove now this nk is greater than or equal to k. So we use this in forming subsequence, so that we write here now nk is greater than or equal to n here. Now here we have k is greater than or equal to n and nk is greater than or equal to k. So we write here nk is greater than or equal to k, nk is greater than or equal to n. So using this, so we write here, and thus now distance between now x and k and x, this is less than epsilon for all k greater than or equal to n here. So this implies that here now this subsequence xn k of xn, now this converges to x as k tends to infinity here. So it means that now here now every convergent sequence has convergent subsequence here. Okay, or you can say that if you take any subsequence of a convergent sequence, then that subsequence is always convergent here. Now the next theorem is about Cauchy sequence in product matrix space. So in this theorem we are going to see a Cauchy sequence in the product matrix space is Cauchy if and only if xn and yn are Cauchy sequence in x and y respectively here. So statement of theorem is this. Theorem: let x comma d1 and y comma d2 be two matrix spaces. A sequence now this sequence here xn comma yn in the product space x cross y is a Cauchy sequence if and only if xn and yn are so in x and y respectively. It means that here xn, then in that case xn is Cauchy sequence in x and yn is Cauchy sequence in y here. Now to prove this, now we consider this metric function here. So proof of this theorem: consider the product metric D on x cross y. Now this is given by D of here x1 comma y1, x2 comma y2. Now these are two ordered pairs. Now x1 comma y1 is first ordered pair and second ordered pair is now x2 comma y2 is equal to now d1 of x1 comma x2 plus now d2 of y1 comma y2, where now this ordered pair now x1 comma y1 and x2 comma y2 belongs to x cross y here. Now here first we are going to assume that now this is a Cauchy sequence in the product matrix space, and we are going to prove that then in that case xn and yn are Cauchy sequence in x and y respectively. Now we write here, assume first that this sequence xn comma yn is a Cauchy sequence, is a Cauchy sequence in metric space x cross y comma d, that is in the product space x cross y with metric d. Then by using definition of Cauchy sequence, we write here, then for each epsilon greater than 0 there exists a positive integer, there exists a positive integer n such that we write here d of first ordered pair is now xm comma yn, okay, then xn comma yn, okay, d of xm comma ym comma xn comma yn. Now this is less than epsilon for all m and n greater than or equal to n here, that is capital N. So this implies that actually using definition of d, we write here d1 of xm comma xn plus now d2 of ym comma yn. So this is less than epsilon for all m and n greater than or equal to n. Now remember, metric function is always non-negative, so d1 and d2 are greater than or equal to 0 and their addition, okay, that is their sum, is less than epsilon. So this implies that here now d1 of xm comma xn, this is less than epsilon, and d2 of ym comma yn, now this is less than epsilon for all m and n greater than or equal to n. So this implies that here now these sequences, that is xn and yn, are Cauchy sequences in x and y respectively. Now for the converse part, now we are going to consider here xn and yn are Cauchy sequences in x and y respectively. Then we are going to prove that now the sequence xn comma yn is the Cauchy sequence in the product space x cross y here. So conversely, assume that xn and yn are Cauchy sequences in x and y respectively, that is in the metric space x and y respectively. Then for each epsilon greater than 0, by using definition of Cauchy sequence, we write for each epsilon greater than 0 there exists a positive integer n1 such that we write here d1 of xm comma xn, this is less than, we are taking here epsilon by 2, so for all m and n greater than or equal to n1. So we write here we are taking positive integer n1 such that we have this, because xn is a Cauchy sequence in metric space x here, okay, and since yn, now yn is a Cauchy sequence in metric space y with respect to metric d2. So we write here, then for each epsilon greater than 0 there exists a positive integer n2 such that now d2 of ym comma yn, that is distance between ym and yn, this is less than epsilon by 2 for all m and n greater than or equal to n2 here. Now taking here n is equal to, now we want to show that now xm comma yn, okay, xn comma yn now is the Cauchy sequence in the product space. So for that we are going to use this n1 and n2. So taking maximum of n1 and n2, and that value is now n here. So actually if you take n is equal to now maximum of n1 and n2, then you can write this d1 of xm comma xn, now this is less than epsilon by 2 for all m and n greater than or equal to n here, and d2 of ym comma yn is less than epsilon by 2 for all m and n greater than or equal to n here. So we write this. Now using definition of d, that is metric function d, we write here d of xm comma ym comma xn comma yn. Actually this is d1 of xm comma xn plus, okay, d2 of ym comma yn. Actually this is the distance between xm and xn here. Now we know that now this is less than epsilon by 2, and this is also less than epsilon by 2 for all m and n greater than or equal to n. So this implies that we write here d of xm comma ym then xn comma yn, now this is less than epsilon by 2 plus epsilon by 2 for all m and n greater than or equal to n. So therefore we write here d of xm comma ym and xn comma yn, now this is less than epsilon for all m and n greater than or equal to n. So this proves that here now this sequence xn comma yn is a Cauchy sequence. So we write here this proves that this sequence xn comma yn is a Cauchy sequence in product space x cross y or x cross y comma d. Okay, thank you.